So we're going to continue to review equilibrium, this time focusing on equilibrium involving gaseous reactants and products, and equilibrium when we've got more than one phase involved. Again, I've taken some example problems from the book Chemistry by Riddell and Navidi, West Publishing, 1990. It was a book that I had on my bookshelf. So, just to start out, right, we have oxygen gas, and say we've got it at 912 torr, right? What is the molar concentration of that oxygen gas? Well, if we start out, right, with our 912 torr, we know that 1 atmosphere is 760 torr, right? If we do that math, it ends up that that is 1.20 atmospheres of pressure, right? We know that our ideal gas law, right? Pressure times volume equals the number of moles times the gas constant R times the temperature in Kelvin. If we rearrange this by dividing both sides by the volume, then we end up with pressure is equal to the number of moles divided by the volume times RT. But the number of moles divided by the volume in liters is our definition of molarity. So therefore, our pressure is equal to the molarity times RT when R is expressed in pressure terms, right? So all we have to do to find concentration, right, if we want to solve for concentration, then we're going to divide both sides by RT. So pressure divided by RT is equal to molarity. So we take our 1.20 atmospheres. Oh, and what I neglected to write down was the temperature that I used, 25 degrees Celsius, or 298.15 Kelvin, right? Our gas constant in pressure terms is 0.08206 liters atmospheres per mole Kelvin, and that's times my 298.15 Kelvin. And when we do that math, I'm running out of space just a little bit, right? When you do that math, you end up with 0.049047, which to three significant figures, which would be 0.0490 molar. And so we can convert pressure terms to molarity terms, and obviously we could go in the reverse direction. If we knew the molarity, we could find the pressure when we're dealing with gases. Let's revisit a reaction that we looked at in an earlier video, our phosphorus pentachloride decomposing in the gas phase to make phosphorus trichloride and chlorine gas. Those form an equilibrium. We had found in our earlier video that the equilibrium constant in concentration terms was 0.04168 at 250 degrees Celsius. The question here is, what is the equilibrium constant in pressure terms? Helps if you can write. Right? What is the equilibrium constant in pressure terms? Well, the first thing we have to remember, right? If we're going to work in pressure terms, we need to be in absolute temperature. And so we find that our 250 degrees Celsius is 523.15 Kelvin, right? That's going to be important. And so we look at the structure of our equilibrium constant, right? So our equilibrium constant is in concentration units, concentration of PCl3, concentration of chlorine divided by the concentration of PCl5. Okay? So we need to convert concentration units into pressure units. And, right, we said that, on the equation we showed on the last time, that pressure was equal to molarity times RT, right? And so if we put that RT, if we multiply RT times all of those concentration units, we will convert them into pressure units, right? So we take that K equals the concentration of PCl3, phosphorus trichloride, times RT, times the concentration of chlorine, times RT, divided by the concentration of phosphorus pentachloride, times RT. Now, we've got RTs appearing in both numerator and denominator, and so some of them will cancel, right? RT divided by RT is 1, but it still leaves us with 1 RT unit. And so if we group our concentration terms, right, let's go to that color, right? We get concentration of phosphorus trichloride, concentration of chlorine, concentration of phosphorus pentachloride, and I'm having trouble fitting it in, but all times RT. And so this term, right, this term is our equilibrium constant under concentration terms. So we can now find that our equilibrium constant under pressure terms is the equilibrium constant under concentration terms times RT, which is our 0.04168 times 0.08206 times 523.15. And so our equilibrium constant in pressure terms is 1.7893, and that will come out in atmospheres to 3 significant figures. It would be 1.79 atmospheres would be our final answer. Here we're considering the decomposition of dinitrogen tetroxide gas to make nitrogen dioxide gas, and note the stoichiometry. The equilibrium constant in pressure terms is given as 0.113 at 25 degrees Celsius. Equilibrium constants are temperature dependent, so you always need to know the temperature at least that the temperature is constant. And here they're giving us an initial pressure of dinitrogen tetroxide as 0.5, and they're telling us that the amount of nitrogen dioxide is 0. This should actually probably be expressed as a pressure, but if the concentration is 0, the pressure is 0. And so we can set up our ice table, right? So if we look at N2O4, and NO2, and we look at our initial condition, we can deal with pressures just like we would concentrations. So we would have 0.5, again with 3 significant figures. We would have 0. Our change would be that if X of this is used up, right? Remember the stoichiometry. Every time 1 mole of this is used, 2 moles of this appears. So if X moles of this is used, then 2X of the product will appear. And so at equilibrium, we have 0.5 minus X, and we have 2X as our representations of our final concentration. And if we put that in the equilibrium constant expression, right, our equilibrium constant is 0.113, and that's going to be equal to 2X all squared, right? Remember the effect of that coefficient, divided by 0.5 minus X. Okay? And if we multiply that through, we're going to get an expression that looks like this. 0.0565 minus 0.113x equals 4x squared. And if we group our like terms, you get 0 equals 4x squared plus 0.113x minus 0.0565. That would be an appropriate expression of our quadratic. Still considering this same system, we've moved our quadratic expression over. Now we need to put it into the quadratic equation. So when we put it in the quadratic equation, we get something that looks like this, right? X is going to be equal to the negative of b, so it's negative 0.113 plus or minus the square root of 0.113 squared minus 4. A is 4. C is negative 0.0565. Paying attention to that sign on C is often a place when errors are made, so be very careful there. And that's all over to A, where A is 4. Right? That is our expression for our quadratic. If we work that through, we get an expression that looks like this at the end, that X is equal to negative 0.113 plus or minus 0.95748, all divided by 8. And if you work that through, you end up with 2 expressions. You get that X equals, make sure I get this right, negative 0.1338, and X equals 0.10556. Okay? So we've got those 2 values of X. Now we have to evaluate them based on how we defined our variables and our final concentrations. Here we are, right? We've brought forward, right? Here's how we defined the concentration of dinitrogen tetroxide at equilibrium. Here's how we defined our concentration of nitrogen dioxide at equilibrium. Here are our two potential values of x. Right? If we look here, we have x as a negative number. If we put it in here, 2 times a negative number gives us a negative concentration. We can't have less than 0 matter. That doesn't make sense. So that number can't work physically, right? And so we look at our other number, 0.5 minus 0.1 will still give us a positive number. 2 times 0.1, that might be reasonable. And so we think, right, that at least to this point, this seems like a reasonable number to work with. And so now we will substitute this in for our variables. So our pressure of N2O4 is going to be 0.5 atmospheres minus 0.10556 atmospheres. And so that then equals, that then equals 0.39444, which to a reasonable 3 significant figures, which would be 0.394 atmospheres after subtraction. Our pressure of nitrogen dioxide was 2 times x, which is 0.10556 atmospheres. And so that ends up being 0.21112, which again, to 3 significant figures, rounding because of our multiplication rule, not because of our adding and subtracting rule this time, would be 0.211 atmospheres. And if we check by putting it back into the equilibrium constant expression, we get our 0.113. So that makes sense. And so those are reasonable answers that we can feel some confidence in. Here we have a different kind of equilibrium. We have an equilibrium between carbon in its solid form, carbon dioxide gas, to make 2 moles of carbon monoxide gas. So we have participants in our equilibrium in 2 different phases, a solid phase and a gaseous phase. And we're given the equilibrium constant at pressure terms as being 14.1 at a given temperature. We're not going to change the temperature in this. And so the question is, if we start with a mixture of carbon as graphite, half an atmosphere of carbon dioxide, and 1 atmosphere of carbon monoxide at this temperature, right, in a container, the first question is, are we at equilibrium? And if not, which direction will we go to achieve equilibrium? That's what our reaction quotient is for, right? So we can use our reaction quotient, right? Let's go this way, right? Right, it has the same expression as the equilibrium constant. So Q is equal to products. So in this case, it would be the partial pressure of carbon dioxide. And then we've got something with carbon, and we'll leave that for a second, times the pressure of carbon dioxide, right? Products over reactants. But in this case, carbon is a solid. And we know that the activity of pure solids and pure liquids becomes 1. And if the activity of pure solids and pure liquids are 1 in a fraction, then that in essence removes itself, and we end up with our Q just being, oh, again, you guys almost let me forget my stoichiometry as I was writing, right? We can't forget to look at the stoichiometry. So our pressure of our carbon monoxide, just messed this all up, haven't I? Right? Gotta pay attention. The pressure of our carbon monoxide product, right, has to be squared. Right? That's what happens when you write faster than you think. You have to be careful. And so now that we've got this right, our activity of carbon is still 1. So now we can reduce our Q to the pressure of carbon monoxide squared divided by the pressure of carbon dioxide. And the pressure of carbon monoxide is 1 atmosphere. Okay, that was mean, making us do all that and then square 1 divided by half an atmosphere. And that makes our Q equal to 2, right? Q is equal to 2, right? And so Q is less than our equilibrium constant, right? And so we have to make Q get bigger. So in order for Q to get bigger, the numerator, the products, we need more products and fewer reactants. So the value of Q being less than the equilibrium constant tells us our reaction has to move toward the right. So when we set up our ice table, right, we've got carbon, solid, we've got carbon dioxide, we've got carbon monoxide, right? So if we're starting, right, initially, the amount of carbon doesn't matter as long as we don't run out. As long as there's always solid carbon there, we're fine. We've got our carbon monoxide at 0.5 atmospheres, our carbon monoxide at 1 atmosphere. Our change, we said we're going to go to the right. So carbon dioxide will go down. Carbon monoxide will go up by 2 times as much. And so at equilibrium, we will have 0.5 minus x is how we will represent the carbon dioxide. 1 plus 2x is how we will represent the carbon monoxide. Still working with the same system, right? We've got our carbon reacting with our carbon dioxide to make 2 carbon monoxide. We just figured out that we could express at equilibrium the partial pressure of carbon dioxide as 0.5 minus x, the partial pressure of carbon monoxide as 1 plus 2x. And so now we can use those in our equilibrium constant, right? So if we take our equilibrium constant, which is 14.1, that's going to equal our products, which is 1 plus 2x. And again, we have to remember our stoichiometry, right? Since that is 2, we have to square it. And that's going to be divided by our reactants, our 0.5 minus x, right? I could write a better 5 than that, just to make it clear. That wasn't much better, but I'll live with it, right? So 0.5 minus x, right? Remember the activity of our solid carbon, our graphite, is 1, and so 1 multiplied in here doesn't appear. And so then if we expand this, we end up, when we multiply it through, we end up with 7.05 minus 14.1x being equal to 1 plus 4x plus 4x squared. If we group our like terms, we end up with 0 being equal to 4x squared plus 18.1 minus 6.05, right? And so when we set up our quadratic, we end up with x being equal to negative 18.1 plus or minus the square root of, of 18.1 squared minus 4. A is 4. C is negative 6.05 all over 2 times 4. Right? And when we work that out, right, if I sort of cut to the chase, we've done a couple of these now, right? We're going to get 2 potential values of x. X equals negative 4.83765 or x equals 0.31265, right? Those are the potential numbers. Again, we compare them back to our definitions, right? So we've got x is negative 4, 0.5 minus a negative 4 would be 9. That would make sense. But 1 plus 2 times negative 4, negative 5, that would give us a negative number. So again, right, we have one number here that doesn't make sense. Right, we have one number, 0.5 minus 0.3, that gives us a positive about 0.2. 1 plus 2 times that is about 1.6. That makes sense. This is the number then that we will move on with to finish our problem. Now remember, we're not done until we reflect back on how we defined our final partial pressures here. So we bring forward our reasonable value for x, and we go back to our definitions that we had before. Right? Let's go that way. Right? And so our partial pressure of carbon dioxide was defined as 0.5 minus x, which would be 0.5 minus 0.31265. That would be equal to 0.18735. But again, there were only 3 significant figures. Subtracting would make us significant in that column. So to our significant figures, it would be 0.187, and we have to remember we're working in atmospheres. We're working in pressure, right? Our pressure of carbon monoxide was 1 plus 2x. So that's 1 plus 2 times 0.31265, which is then equal to 1.6253 atmospheres, right? If the 1 was 3 significant figures, then we would be adding in this figure. So the best would be then, right, the best representation would be about 1.63 atmospheres. When I put the unrounded numbers, right, my unrounded numbers, right, so if I used this number and put them back in the KP, I got my KP of 14.1, so my numbers checked out and we can feel confident. So I hope these problems helped you with some concepts on gaseous equilibria and on heterogeneous equilibria.